this video, we're going to talk about logarithms and exponential equations and functions. So let me go ahead and get the whiteboard up. There we go. So let's go ahead and review our properties of logarithms. Log base A of x, y is equal to log base A of x plus log base A of y, because what we reviewed last time, the a to the x times a to the y is equal to a to the x plus y. Logarithms have to do with exponents. So multiplication of like bases turns into addition of exponents. Similarly, log base A of x divided by y is equal to log base A of x minus log base A of y. It should make sense that if multiplication turns into addition, that division should turn into subtraction, and the part that's negative should be the part in the denominator because it has a negative exponent. Log base A of 1 over x is going to be negative log base A of x. That's a specific example of log base A of x to the n is n. Log base A of x. Log base A of anything of 1 is 0 no matter what the base is. And log base A of itself is 1. And we might have a change of base formula here, that if we want to change log base A of x into log base B, that's going to happen by this formula, which we're usually going to use to change it into either natural log or common log, because those can be entered in on our calculator. Don't think that I missed any log properties. This one here can be used for negative exponents like I did up here. It also can be used for fractional exponents for roots, like we talked about last time. So let's go ahead and let's jump into our problems today, explain the relationship between logarithmic functions and exponential functions. They're inverses of one another. They undo one another in the same way that multiplication and division undo one another, addition and subtraction undo one another. So if I take log base A of a to the x, they're going to undo one another and give me x. If I take a to the log base A of x, they're going to undo one another and give me x. But let's give it in a more formal definition here. If a to the x is equal to b, then log base A of b is equal to x. We can rewrite it that way, or what was our answer over here is our input into our logarithm. I keep the same base, and what was my input here becomes my output over here. So when I want to solve for the exponent in an exponential equation, I can go ahead and write it this way. So let's put together everything from 1.4 and 1.5 in what we call the triangle of power. See if I can remember this. So I'm going to have, if I have an unknown in any one of these positions, I have a way to, I'm just going to use this as an example. So this is my triangle of power that says 2 to the third is equal to 8. That's one of the ways that I can express this relationship between 2, 3, and 8. 2 to the third is equal to 8. It's also true that the cube root of 8 is equal to 2. We studied those in 1.4. But now we're going to talk about in 1.5 that log base 2 of 8 is equal to 3. That's the third way that we can express that relationship. They all say the same thing, that 2 to the third is equal to 8. The cube root of 8 is 2, and log base 2 of 8 is equal to 3. They all say the same thing, but look at how each one of them is solving for a different box in the triangle of power. Do you see that? That this one solves for the box that's on the lower right here. This one solves for the box in the lower left, and this one solves for the box that's on top. This solves for the power, the logarithm. This one solves for the base. And this one solves for let's just call that the solution for right now. I don't have a better name for it, but what 2 to the third is, right? So there it is. That's a nice visual for people that have a visual representation of numbers. So we can use the triangle of power for other things here. I'll set it up and I'll use it here as an example of 3 to what power is equal to 81. So that's 3 to the fourth power. So log base 3 of 81 is equal to 4. What questions are you answering when you evaluate log base 5 of 25? Log base 5 of 25 is answering what is the power on 5 that gives me 25. So if I have 5 and I have 25, I want to know what the power is here on 5 that equals 25, and the answer is going to be 2. Log base 5 of 25 is equal to 2 because log base 5 of 5 squared is going to be equal to 2 times log base 5 of 5. Log base anything of itself here is always 1. 2 times 1 is 2. What is the value of the base in the natural log of x? It is base e. E, Euler's number e. Call it the exponential number sometimes, or the exponential base. So when we talk about something that is an exponential equation, if we don't define the base, we assume the base is e here, and it's 2.71 approximately. It's like pi, that's an irrational number, that's a non-repeating, non-terminating decimal, but just like we approximate pi with 3.14, e is approximately 2.71. Explain why logarithms help us solve exponential statements. We just showed that with the triangle of power. So we've already solved number 5 just a second ago with the triangle of power. Let's look at ln of e to the 5.7. So I told you that there's log base a of a to the n is always equal to n, right? The bases are the same here, they're base e. So my answer is 5.7. E to the negative ln of x is going to be e to the ln of 1 over x, like that. And these are inverse functions that are going to undo one another, and I'm going to be left with 1 over x. you don't believe that, let's try it a different way. E to the negative ln of x is the same thing as 1 over e to the ln of x. E to the ln of x is going to be x. For log base 2 of 2 squared. Okay. Log base 2 of 2 squared is going to be 4. No, it's going to be 2. Sorry. The base 2s are going to undo one another. The 2 is going to come out front. 2 times 1 is 2. 4 squared is 16. Write the single simplified logarithm, so we're going to condense. 4 log base 3 of 2x minus log base 3 of y squared. So we're going to write the powers up in here first. This is 16x to the 4th. Log base 3 of y squared. So log base 3, 16x to the 4th is positive. It stays in the numerator. Y squared is negative. It goes to the denominator. 2/3 ln of x plus 3 ln of 2y. So this is going to be ln of x to the 2/3 plus ln of 8y to the 3rd. So this is going to be ln of 8y to the 3rd cube root of x squared. X to the 2/3 is the same as cube root of x squared. We have 2x log base 2 of 3 plus log base 2 of 5. So this is going to be log base 2 of 9 to the x plus log base 2 of 5 is log base 2 of 5 times 9 to the x. You could have left this as 3 to the 2x if you want. That would have also been the same thing. Let's move on now to number 12. Number 12 asks us 3 ln of xy minus 2 ln of x squared y. I might actually want to expand this first before condensing. So this is 3 ln of x plus 3 ln of y minus 4 ln of x minus 2 ln of y. 2 times 2 is 4. So I've got negative ln of x plus ln of y be ln of y over x. So another way I could have figured that out? Absolutely. There's lots of ways to figure these out. So I have ln of x to the 3rd, y to the 3rd, divided by x to the 4th, y to the 2nd. This is going to give me y. This is going to give me x. And I get the same answer. Solve the problem if possible. If the problem cannot be solved, explain why. 5 to the x is equal to 25. So our triangle of power should help us here. 5 to what power is equal to 25? The answer here for x is x is equal to 2. You know that 5 squared is 25. We can write this as log base 5 of 25 is equal to x. Log base 5 of 5 squared is equal to x. I may have actually solved this problem earlier, not knowing it was a problem in the assignment. There it is. 5 to the x is equal to negative 5. There's no solution to this because I can't ever raise 5 to a power and get a negative number. That won't work. I can get numbers bigger than 5. I can get numbers equal to 5. I can get 1. I can get fractions that have denominators that are powers of 5, but I can't ever get a negative 5 unless I have a negative out front of the 5 to the x. Nothing by multiplication or division is going to change by 5 or by a power of 5 is going to change the sign to a negative. So there's no solution here. 5 to the x is equal to 0. Nope, can't do that. The only way that I multiply and get 0 is if I'm multiplying by 0 and I'm multiplying by powers of 5. I'm not multiplying by 0. So there's still no solution here. That 5 to the 0 would be 1. So now 5 to the x is equal to 2/10, which is 1/5, which is 5 to the negative first. 5 to the x is equal to 5 to the negative first. So by the 1-to-1 property, since exponential functions are 1-to-1, if the bases are the same and the outputs are equal, then the inputs have to be equal. 5 to the x is equal to 1. 5 to the x is going to be equal to 5 to the 0. X is going to be equal to 0. Now we're going to solve 3 to the x minus 6 is equal to 2. So we don't have the same base anymore, so we're going to have to use logarithms here to get an exact answer. So I'm going to take log base 3 of both sides. And that's going to return the exponent of x minus 6 is equal to log base 3 of 2. And so x is going to be log base 3 of 2 plus 6, and that's my exact answer. Four to the 2x minus 5 is equal to 3. So this is going to be log base 4 of 3 is going to be 2x minus 5. 2x is equal to log base 4 of 3 plus 5. X is equal to 1/2 log base 4 of 3 plus 5/2. 2 to the 5x plus 6 is equal to 4. So 5x plus 6 is equal to log base 2 of 4. Remember that 4 is a power of 2. So we can rewrite that. That's 2 because 2 squared is 4. I'm going to subtract 6 from both sides. 5x is negative 4. And x is equal to negative 4/5 or negative 8/10 if you want to express it as a decimal. Six to the x plus pi is equal to 2. So x plus pi is equal to log base 6 of 2, and x is equal to log base 6 of 2 minus pi. Now we have 1/6 to the negative 3x minus 2 is equal to 36 to the x plus 1. I'm going to write them with a common base of 6. 6 to the negative first is equal to the negative 3x minus 2. 6 to the second to the x plus 1. I'm going to multiply the exponents here. And because I have my one-to-one property that says that if these exponential statements are equal and their bases are equal, their exponents have to be equal. That's going to be x plus 2 is equal to 2, x is equal to 0. So the only way that these are going to be equal to each other is when x is equal to 0. It's the only time. Negative 15 is equal to negative 8 ln of 3x plus 7. Subtract 7 from both sides first to isolate my logarithmic expression. Now I'm going to divide both sides by negative 8. That's going to give me 11 over 4 is equal to ln of 3x. I'm going to have to reverse the process here and say 3x is equal to e to the 11 over 4. So x is going to be e to the 11 over 4 divided by 3. Or I could write that as 1/3 e to the 11 over 4. (24) is 2 to the x is equal to 3 to the x minus 1. We've got a problem here where the bases are different. So one of the only ways to solve this is to take a log of something. I'm going to use ln. You could use log base 10. I'm going to take ln of 2 the x equals ln of 3 to the x minus 1. So x ln of 2 equals x minus 1 ln of 3. When I have to distribute, x ln of 2 equals x ln of 3 minus ln of 3. So we're going to get our terms with our x's together. X ln of 2 minus x ln of 3 is equal to negative ln of 3. Since ln of 3 is bigger than ln of 2, I'm going to divide everything by a negative 1 here. Get the order of subtraction to be something that's not going to give me a negative. That. Now this is going to be ln of 3 minus ln of 2 is equal to ln of 3. So x is going to be equal to ln of 3 divided by ln of 3 minus ln of 2. Does not matter what I make the base here, but we typically use natural log because it's the least number of letters for us to write. 8 equals 4 ln of 2x plus 5. Divide by 4. 2 is equal to ln of 2x plus 5. 2x plus 5 is equal to e to the second. 2x is equal to e to the second minus 5. X is equal to e to the second minus 5 divided by 2. I believe that those are all of the problems for this unit. That's it. Next time that we come back, we'll start talking about chapter 2, which is basic skills for calculus. See you in the next video.